today I'm going to talk about methods of proof. So okay. So first, let's talk about the direct method. So this is something we've talked about already. So essentially, I'm going to give a bunch of different methods, and then I'm going to give some examples. And then first, I'm going to describe what you do. Okay, so to prove P implies Q. So what you do is you assume P and try to conclude Q. Okay? So let me give you an example. Okay, so here's an example statement. So in this example, we'll prove that for every natural number, and so the natural numbers are going to start at 1, 3 divides 4 to the n minus 1. Okay, so this is what we're going to prove. So let me make a little remark here. So let's note the form of this statement. The form of this statement is for every n in the natural numbers, 3 divides 4 to the n minus 1. Okay? And so this is equivalent to this is the same as for all n in the natural numbers implies, so this is what we talked about quantifying over sets, 4 to the n minus 1. Okay? So that's what we are going to show. Okay, so that's what I wanted to say, is that this is really an implication. Okay, so proof. So in these direct proofs, we just start with the assumption. Okay, so the assumption is suppose n is a natural number. Okay? And now we need to conclude that 3 divides 4 to the n minus 1. Okay? So the geometric sum, so the geometric the geometric sum formula gives the following. It says that x to the n minus 1 is equal to x minus 1 times 1 plus x squared plus all the way up to x to the n minus 1. So this is a formula from Calc 2. Okay. So really, it may be more familiar if you divide this, and then it gives you a formula for summing that sequence, right? Okay. So so this implies. So this means that 4 to the n minus 1. Well, this is 4 minus 1, and then we do 1 plus 4 squared plus dot 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 plus 4 to the n minus 1. Yeah, did someone have a question? No? Okay. Okay, and this thing here is just 3 times some stuff here. Okay, it doesn't really matter what it is, but it's 3, so 4 minus 1 is 3 times 1 plus 4 squared, etc. Right? So by the definition of divisibility, so let's do it over here. So by the definition, that's an F, of divisibility, 3 divides 4 to the n minus 1. Does that make sense? Okay. Okay, so that was a direct proof. Okay, and I'm going to end the proof with this little thing here. Okay, so now I'm going to, we talked about contrapositives before. I'm going to give a contrapositive, how to use the contrapositive now. So, of contrapositive. So some of the names that I'm giving for these are not standard, but I think if you were to say them to any mathematician, they would understand what you meant. Okay, so names for these type of things may vary. So to prove P implies Q, we prove not P, or not Q implies not P instead. And what we talked about before is that P implies Q and not Q implies not P. We showed that they were logically equivalent. Okay. So sometimes the statement not Q implies not P is an easier one to do. So here, let me give you an example. Okay. So we'll prove that for all natural numbers, n, if or let's say natural numbers, let's do a and n. A and n. So if a to the n is odd, then a is odd. Okay? So this is the statement we want to prove. So here's the proof. Okay, so we will prove the contrapositive. We will prove this by contrapositive. Okay, so I'm stating the method of proof that I'm going to use. Okay, and so the original statement, I always forget to do that. So the statement is, okay, if a to the n is odd, this implies a is odd. Okay, so the contrapositive is we negate Q, and that implies the negation of P. So if A is not odd, it's even. So A is even implies A to the n is even. Okay, and now we have this contrapositive statement, and now we're just going to proceed as if it were a direct proof. Okay, so suppose A is even. Okay, so by definition, this means that there exists some k in the natural numbers such that, okay, we'll say what it means to be even. It means it's 2 times something. And I'm going to continue the proof over on this side. Such that A is equal to 2k. Okay, so that's what it means for it to be even. Okay, and so now I'm going to do one of these things where we just go down and get a sequence of equalities to arrive at our conclusion, like we were doing before. Okay, so this means that a to the n, So this is the thing that we're trying to, so this is our goal. We want to show that this thing is even. And that's the same thing as if it was 2 times something. So this is equal to 2k to the n, which is equal to 2 times 2 to the n minus 1, k to the n. Okay, so by the definition of divisibility, uh, 2 divides a to the n, and hence a to the n is even. Okay, so let me make a little remark here. So how did I get from this line to this line, right? So here, I just used the power rules, right? So this is just from Calc 1, or before Calc 1, right? It's just that here, right? So 2k to the n, this is really 2 to the n, k to the n, right? And then I could break this up further. 2 times, this is 2 to the 1, 2 to the n minus 1 times k to the n. So that's what I did there. Okay, does that make sense? Everyone seems cool with this? Okay. All right, so let me show you another method. So from here, this line to this line? Yeah. Okay. So here, so here's the rule that I used, right? So here, we're using that 2 to the, so I'm using that, so like if I have any bases, b to the x times b to the y is b to the x plus y, right? Here, b is equal to 2, x is equal to 1, and y is equal to 1. All right, y is equal to n minus 1. So for this one here, so I broke up n into, so I broke up n into 1 plus n minus 1. All right, does that make sense? Okay. Okay. Yeah. Okay. So let me show you another method. So this is a method by cases. So I'm going to give another proof. Any more questions on the previous one? Okay, so this is a new one. Okay, so here, so we break up, so show P implies Q. We introduce cases so that one of each, so that, I don't know, cases P1, P2, P3, etc. Let's say all the way up to Pn, so n some natural number, such that P is equal to P1 or P2 or P3 or all the way up to Pn. Okay, so we break it up into a bunch of things, and then prove a bunch. We may do a bunch of different proofs. Pi implies Q for each of the cases. Okay, so essentially we break it down into a bunch of different things which we know, one of which must be true, and in each of the cases we will prove the statement. Okay, so so let me give you an example so you guys can see what I'm talking about. Okay, so here's an example. So in this example, we will prove. Oh, also, let me make another. Okay, so before I do this, let me just make a remark here that this is an if and only if. Okay, so these statements here. By the way, so I just wanted to tell you that this will come up later, but this is, it's an if and only if statement here. We only proved one direction, right? But they're equivalent. Okay. Anyway, back to this thing. Okay, so we will prove for every n in the natural numbers, n2 divides n times n plus 1. Okay, so let's prove this thing. So what are the cases that I could do here? So here's the proof. Okay, so in this case, prove this by cases. So if n is in the natural numbers, then n is either even or odd. Okay, so those are the two cases that we're going to consider. We're going to suppose at one point that it's even, and then we're going to do the proof. And then we're going to suppose in one case that it's odd, and then we're going to do the proof. So we're really going to do two proofs. So here, there'd only be two of these things, right? And then it'd be even, one would be the case that it's even, one would be the case that it's odd. Every natural number is either even or odd, right? Okay, so let's do the even case. So in the even case, we suppose n is even. Okay, so by definition, this means that n is equal to 2 times k for some k in the natural numbers. All right? All right. So now what do we want to do? We want to look at, this is the thing that we're trying to conclude. Okay? So let's write down what this thing is. This gives the following. And now I'm going to do another string of equalities. Okay? And I'm going to show that 2 divides n times n plus 1. N times n plus 1. So this is 2k times 2k plus 1. And so this thing looks like 2 times the quantity k times 2k plus 1. So it's 2 times some junk, right? So that means that it's even. Hence, n times n plus 1 is even. Okay, so this is the first little subproof. Okay, so sometimes even when you're doing these cases, you could even, like, if you wanted to make it really easy on the reader, you could indent this whole thing, right? And then it'd be really clear, so you can just kind of like look at the page and then see where the case starts and where the case ends. It's kind of like, where you have like coding standards, right? Same idea, right? So for a programming class, you try and make it nice and you try and comment your code, right? And that's kind of like what we're doing. Okay, so the odd case. Okay, so in the odd case, we suppose n is odd. Okay, so we're going to just start a direct proof here. So by definition, so there exists some k in the natural numbers such that n is equal to 2k plus 1. All right. Now, we just do the thing that we did again. So hence, and we continue, right? N times n plus 1. So So this is equal to 2k plus 1 times 2k plus 1 plus 1. So this is equal to 2k plus 1. And I just kind of, fill out the paperwork for this proof. Okay, so it's like, you kind of know how it's going to go, but you just got to do it. All right. So here this is divisible by 2. So this is 2 times 2k plus 1 times k plus 1. So 2 divides n times n plus 1, and we're done. Okay, and so at the end we have this case and we have this case. Okay, so since both cases are true, so I'm writing since we proved both cases, the result follows. We showed that n times n plus 1 is always divisible by 2. Does that make sense? Yeah.
It's always divisible by 2 because 2 times something.
It's 2 times something. That's the definition of divisibility.
Yeah.
So that it factors as 2 times some junk, right? We don't care what the junk is. It just needs to be 2 times whatever. That means it's divisible by 2. Yeah, it could be whatever. Doesn't matter at all. We don't care. Yeah. Yeah, not caring is important sometimes. Because you don't want to get bogged down on like thinking about what the leftover stuff means. Okay, so let me do another type of proof technique. Okay, so we did the method of contrapositive. This is kind of similar. Method of contradiction. Okay, so to prove P implies Q, we will show that not P, or P and not Q. Remember the definition of P implies Q is not P and not Q, is false. Is false. So in other words, we suppose P and not Q and show that it gives us some nonsense. P and not Q, and try to derive nonsense. So you want to find some statement that has some sort of contradiction. Okay? And so when you show that, you're showing not this, which is the same thing as P implies Q. Okay, so let me give you an example. Here's an example. Okay, so we will show that if n is a natural number and n cubed plus 5 is even, or is odd, then n is even, or then n is odd, excuse me. Sorry, then n is even. All right, so here's the proof. And so you can tell that you're going to have a proof by contradiction because we say something like, okay, we're going to do this proof by contradiction. You can even write that out. We will do this proof by contradiction. A short way of saying that is you could say, suppose not. And that's a very common thing to say before proofs by contradiction. So this indicates that you're going to do a proof by contradiction, right? So So this means, right, and so let me do a little quantifier calculation here. So the statement is, for all n in the natural numbers, right, n cubed plus 5, if this is odd, this implies n is even. Okay? So if I were going to do the negation of this, so when we do a negation, right, we flip the quantifiers and then we negate this. Okay? So the negation is, so there exists an n in the natural numbers such that p and not q is odd and n is even. Or n is not, so not q, and n is odd. Okay? So this is a statement that not this. So we do p and not q. Okay? Okay. Okay, so okay, so now what we're going to do is we're going to take this negation and we're going to derive a contradiction. So we're going to show that this is false. Okay? So let m, so since there exists one, let m be such an integer, an odd integer with m cubed plus 5 being odd. Okay, and so by the remark that I said that, m to some power is odd if and only if m is odd, we know that, this thing must be odd. Okay? Since powers of odd numbers are odd, of odds, odd numbers are odd, m cubed, okay? M cubed is odd. Okay, so this means m cubed plus 5 is an odd number plus an odd number. M cubed plus 5 is an odd plus odd, which is even. If you add two odd numbers, it's even. All right? But what did we do? Right? So what did we suppose? We suppose that here, n cubed plus 5 is odd, or in particular, m cubed plus 5 is odd for a particular one. So this is like there exists one, and then we flagged the variable. We said that we picked a particular one, right? Okay, and so which is even. So this contradicts. We got some nonsense, right? This contradicts that m cubed plus 5 is even. Right? And we're done. Right? So we've derived a contradiction. Right? We showed that if it wasn't the case, then we would have m cubed plus 5 being odd and even at the same time. Yeah?
Can you give an actual value?
So that's a good observation, is that proofs by contradiction are what are called not constructive. And some people don't like them, right, sometimes because they don't give you things. But yeah, you could do a proof like this. I think that would give you something. Yeah. That's a good observation. Okay. So let me do one more thing. Okay. So what time does this end? 40. Okay, great. Okay. So then let me just do one more thing about uniqueness statements, and then we'll go on. Any more questions on this before I move on? Yeah.
I guess I'm just kind of thrown by that last sentence, just like what?
Okay, so like, sorry. This contradicts. Sorry, odd. Thank you. Yeah. Thank you. Yeah. All right. Good point. All right. So, okay, so let me just start with uniqueness statements. Okay. So, usually these go with existence statements. So there's kind of two parts, right? So you could say that there exists some x such that some proposition holds, or some predicate p of x, right? If the thing is unique, it's that whenever p of x holds, right, it's the only thing. So, okay, so we're actually going to introduce a new symbol here. So this symbol here is a new quantifier, and it says there exists a unique. And I'm going to repeat what I said before. So, so there's kind of two parts to this. There's two parts. There's existence and uniqueness. And so whenever you have something, so let me write this. So let me just show you what this, how to read this in English. So if I write, there exists a unique x such that that's an exclamation point, p of x. So this means this is, there exists a unique x such that p of x, such that p of x is true. Okay? Uniqueness is the following thing. So uniqueness is that if, so if x satisfies p of x and y satisfies p of y, then x is equal to y. So this statement here is saying there is a unique x such that, or sorry, let me say this. So if an x exists such that p of x, then it is unique. Okay, and this is a really common thing that people ask you to do, is to show uniqueness of something. Is like, and so in the homework we have a uniqueness statement. Okay, and so how to prove this? So how to prove uniqueness statements? So what you do is you suppose there exists x and y satisfying p of x and p of y, right? So you suppose something that, you suppose p of x and p of y for some x and y, and then you try to conclude x is equal to y. Okay? So let me give you an example. All right, here's an example. Okay? So show that there is a unique, so if y is, sorry, I don't want to say, I'm trying to just do the uniqueness part, so I keep saying the existence and uniqueness, but I'm just trying to isolate the uniqueness. So if y is a real valued function of one variable, one real variable, so like in calculus, which is differentiable, So all this stuff, I'm just saying so that what follows makes sense, and satisfies the following equation. So I'm going to write down a differential equation now. dy dx is equal to e to the x squared sine y, or sine x, and y. So it's a function here. Y of 0 is equal to 1. Then it is unique. Okay, so this is what we want to prove. Okay, so here I'm just saying if you're in a situation where derivatives make sense and you're like calculus, this is like calc 1 type thing, right? And you have this differential equation, then it's unique. Okay? So now we're going to do the thing that I said over here. So P of x is this thing. Okay? So what we'll do is, to show uniqueness, we suppose that there's two things, and then we show that they're the same. So here's the proof. Okay, so we suppose there exists some y1 and y2. So these are two functions of a single variable that satisfy star. Okay, and star I'm going to do like this. So a lot of times we like to label equations or conditions and then reference them later so that we don't have to copy them down all the time again. And there's actually shorthands in LaTeX for doing this. And so these are label and reference things. Okay? So this implies, so note that there's two conditions here. Okay? So this implies that dy1 dx is equal to e to the x squared sine of x, and dy2 dx is equal to e to the x squared sine of x. Okay? So now I'm going to try and conclude that y1 and y2 are the same. Okay? So what we can do is we can subtract these. Subtracting these equations gives the following equation. d dx of y1 minus y2 is equal to 0. Okay? And so we know from calculus, this implies that y1 minus y2 must be a constant. So this implies C for some in R. Okay, and we know that it's real because I said it was real valued. Okay? Now, one thing to know is that I give you two things. So this thing is really an and statement. I'm saying this is true and this condition is true. When I plug in 0, I'm supposed to get 1. So in order to finish a proof, a lot of the times you should make sure that you use all of the things that are given to you. Okay? So here, what I can do is plugging in in 1, x is equal to 1, gives the following. y1, y2, and then I'm going to plug in 1 into c, right? So when I plug in 1 into c, that's just c, right? Because you plug it into a constant. Okay? So this is 1 minus 1, and this is 0. So this is equal to, I can do it like this, 1 minus 1, and that's 0. Okay, so C is equal to 0. Okay, so this shows y1 minus y2 is 0. Or, in other words, y1 is equal to y2. Okay, so this is what we wanted to do, right? So we wanted to suppose that there were two solutions, right? Then we used the conditions that we had here, right? This part here, which will vary from proof to proof. But eventually, we're going to conclude that y1 is equal to y2. And that's what I mean by a uniqueness statement. Yeah? Oh, sorry, 0. Yeah, the initial condition was at 0. Thank you very much. Yeah. Plug in at 0. Thank you. Yeah. Good point. Okay.
That one is 0 minus 0. It would change something.
No, it wouldn't be 0 minus 0 because y1 of 0 is still 1. So the point here is that it doesn't matter what I put here. So actually, I could change this to whatever I wanted here. And in the proof, and I could change this function to whatever we wanted here. Right? But the point is that we ended up getting that the difference was a constant because we knew the derivative was 0. And then we could actually figure out what the constant was by plugging in the conditions. So those are called the initial values for this differential equation. Right? And since they're the same, we knew that this constant had to be 0, which said that it was unique. OK. So with the last bit of time, we're going to do some exercises. Okay, and then that'll hopefully clarify some of these things. Okay, so exercises. Okay, so from handout 2. Okay, from section 1, you can try 6a or 7. Well, let's see, not 7. Let's not do 7. Let's do 6a or 9. And from section 2, let's do 1, 3, 4, and 5. Okay, also, okay, here's another problem that you could do you can do. So verify that H, that the set of functions of one variable. So I'm going to write down the functions now. So this is this H. This will be the set of x plus c, where c is a real number. Forms a group under with star being composition. Okay? This is the composition of functions. So this is one function being plugged into another function. Okay? And to do this, you need to really verify you need to do 4 little separate proofs. Right? So let me make a little remark about this. So does everyone know what I mean by composition of functions? Let me just make a remark here. F composed with g of x. So this is equal to f of g of x. That's all that I mean. Okay? So like we can take those functions, then we can plug them into each other. And that'll give us a group operation. Okay? So you need to check the following, right? The closure under composition. Two, the identity, existence of identity. 3, the existence of inverses. And then 4, so these are the group axioms, associativity. And so like there should really be 4 proofs that you do to do all of this. Okay, so there should be one little proof for each of those things. Okay,